So hi and welcome everybody to the lecture titled 5G Waveform and Multiple Access Techniques. In this lecture we will be discussing and reviewing the main waveforms that have been proposed for 5G technologies, the advantages and disadvantages of each one of them, and how to generate them using the block diagram at the transmitter and receiver, and then explain to you and show you why the community has decided to choose OFDM CB with windowing for 5G, and how is it flexible to support different use cases and different scenarios. So the first thing, the outline of this is going to be structured as follows. First, we'll give you a summary of the things that have been decided regarding 5G. Then we'll discuss waveforms and multiple access techniques evaluation and recommendation, the key waveforms, physical layer waveforms comparison, multiple access techniques comparison and recommendation, and then additional information on physical layer waveforms, how to design them, the transmitter and receiver, single carrier waveform, and multi-carrier OFDM-based waveform. Additional information related to multiple access techniques will be given as well, including orthogonal and non-orthogonal multiple access. So first thing first, let's give you a summary of the things related to waveform and multiple access in 5G. 5G is agreed to support diverse use cases. It's not like 2G, 3G, 4G, where you have only one use case and you try to satisfy it. You have Internet of Things, massive Internet of Things communication, critical, high reliable, low latency Internet of Things application, and you have the enhanced mobile broadband communication. So basically you need to support all at the same time. So there is no such single technology that can meet all these requirements simultaneously. To achieve that, we proposed configuring the subcarrier spacing and symbol duration in OFDM and make it so flexible so that we change it according to the scenario. OFDM family, OFDM waveforms are found to be suitable for mobile broadband and beyond, mainly because they can be integrated efficiently with MIMO, spatial multiplexing, to achieve high spectral efficiency. They are scalable to wideband with lower complexity. With lower complexity, put under it two lines to highlight it. Lower complexity. Any method that's so complex, although it can achieve some good advantages in some areas, but if it is so complex, we don't prefer to use it because it's gonna cost us a lot. So we try our best to come up with a method that can bring some advantages while not bringing too much complexity. CB OFDM multiple access for 5G downlink is considered to be used, and with windowing, of course, and filtering to make the out-of-band emission low, and single carrier frequency division multiplexing, single carrier FDMA for scenario requiring high energy efficiency, which is for the case when you want to let the users communicate with the base station. In this case, we use different waveforms that are more spectrally, more energy efficient than OFDM. Resources spread multiple access for use cases requiring asynchronous and grantless access. Additional waveform and multiple access options are included to support specific scenarios. So you are not limited only to OFDM, but you can also use some other waveforms which are basically related to OFDM. We call them the I50 family, all the waveforms that use I50. In downlink, we recommend using OFDM, and as a multiple accessing scheme, you can also use OFDM-A. It's OFDM, but for multiple users. Enhanced mobile broadband communication for frequencies at 6 GHz and below, you use OFDM and single carrier frequency division multiplexing. We will explain the differences between them when I tell you what's single carrier FDMA. You must be able to answer that and know the difference. And for unlicensed and small cell uplink, we can use OFDM and OFDM-A as a multiple access scheme. In wide area Internet of Things, in the uplink you use single carrier FDE. And multiple access RSMA. In millimeter wave, uplink can be OFDM or single carrier FDM. Multiple access OFDM-A or single carrier FDM-A. In high reliability services, in the uplink you can use OFDM, single carrier FDM-A, multiple access OFDM, single carrier FDM-A or RSMA. Basically, the difference in the uplink, in downlink, most of them they agree on using OFDM. Sometimes single carrier, but in the uplink we always prefer to use something other than OFDM because OFDM has high peak to average power ratio, and high peak to average power ratio kills the battery and the range will be low. So basically these are the issue: waveform and multiple access evaluation. So what's the key motivation for waveform? We need to support wide range of use cases, including enhanced mobile broadband, massive Internet of Things, and high reliable Internet of Things. The requirements of each one of them: enhanced mobile broadband requires higher throughput, higher spectral efficiency. Massive Internet of Things, you have massive number of low power, small data burst devices with limited link budget, while for higher reliability Internet of Things devices, you have services with extremely lower latency and higher reliability requirements. So one single waveform can never meet all these requirements simultaneously. That's why, due to this diversity in the requirements, we need to consider different solutions and map each solution to one case. Accommodate different numerology optimized for specific deployment scenario. Now let's define the word numerology here for the ones who don't know. Numerology here, simply put it like this: OFDM but with different subcarrier spacing. OFDM with subcarrier equal 15 kHz is numerology number 1. OFDM with 30 kHz is numerology number 2. With 30, with 40, with 45, with 60, and so on and so forth. Basically, numerology is a term that refers to subcarrier spacing in OFDM. Minimize signaling and control overhead to improve efficiency. These are the motivation for the work and research on waveform. The problems that we are trying to solve cannot be solved by a software or the application layer or network layer. There is no way you can solve them. You can only solve them at the physical layer level. And there are thousands of companies around the world who try to come up with solutions to solve these problems and meet with each other on the 3GPP standardization organization, and they try to discuss and evaluate all these waveforms. So if you want to summarize the requirements of each use case, in enhanced mobile broadband, we need lower latency scalable numerology, self-contained TDD subframe structure, new TDD for massive MIMO, integrated access backhaul and device to device. For wide area Internet of Things, you need lower energy waveform, optimized link budget, decreased overheads, and managed mesh. Who puts these requirements? ITU, International Telecommunication Union organization. They say after 10 years, the 6G will require these requirements. Who responds to ITU? The standardization body. Who responds to the standardization body? The companies, the academia, the active people, basically. They consult them. What do you think? Which technique can we use? Can we use this? Come and sit here and meet. Every month they meet with each other. For 2-3 years, continuous meeting each month. Like this, and a guy representing Qualcomm, a guy representing Ericsson, not one, maybe group. And they meet with each other and they vote. Like the people vote for the president. They vote. Who does support OFDM to be used for 5G? They raise their hands. Only those people can vote. Normal people cannot. The ones who attend the meeting and part of the standardization body. Of course, they make alliances. People in Ericsson come and talk to the people in Qualcomm. What do you think? We have 100 patents on OFDM. Qualcomm, they have 200 patents on OFDM. What do you think? We should push this. We should convince the people to use this, because if they use it, they will keep buying our patents. We keep buying, making money. If we lose it, we are out of the game. So it's politics. On the whoever makes his hand first, whoever puts the policy here, the board will follow him, because this is standardization. Everybody's gonna be using it. Everybody. Whether you are in Pakistan or China or Japan or Turkey or wherever, you are going to keep paying for the patents produced by X company related to the OFDM waveform that's used in this patent, because it will be used with each and every mobile phone. So each user must pay for that. So politics. Serious people. You might be in the future, you might be among those people. Who knows? If you understand these things and you go to a company, high profile company like Nokia, Ericsson, Huawei, these companies that participate in the standardization, and you will be the representative in that company, and you want to, what's your mission? Try to come up with good techniques and convince the community with it and vote for it and make it in the standard, so that your company keeps making revenue out of these patents and licenses. So millimeter wave, sub 6 gigahertz and millimeter wave, common MAC. We need to have common medium access channel, access and backhaul. Millimeter wave beam tracking is very critical issue. High reliability. We need lower packet loss rate, extremely low bit error rate, lower latency, optimized physical pilot, HARQ, and efficient multiplexing. These are the general requirements. Key design targets. In general, these are the requirements that we always need more of them. Higher spectral efficiency can be supported by MIMO. Ability to efficiently support MIMO and multipath robustness. I told you, when you increase your data rate, what's the problem you face? You increase your data rate, you reduces your sample period, yes? Quickly it starts shifting, means you have larger delay spread. Larger delay spread means severe multipath. You need to overcome this. You need to support MIMO as well, because MIMO is the only way to increase your spectral efficiency. What else we need? We need lower in-band and out-of-band emission. I told you the side loops. We need to cut them. We need to kill them. We need to reduce them as much as we can, because if we don't reduce them, we cannot utilize the spectrum, which is very precious and very expensive, and we buy it from government for millions of dollars. If we don't reduce them, we cannot put 10 users in 10 megahertz. We can only put 5. But if you can put 10, you save half of the bandwidth, you save 500,000. Yes, this is the impact of this. It's true, tiny, small, dealing with OFDM, but when you think of it, each user is asking for thousands of OFDM symbols, and there are thousands of users, and this tiny thing, when you multiply it by these numbers, become huge and large. If you can reduce a little bit of it and multiply it with these numbers, become significant and large. Enables asynchronous multiple access. Because the Internet of Things cannot wait for us to keep synchronizing and handshaking with the base station. We need to measure the data, sense it, and quickly send it to the network without getting any permission. Lower power consumption. Why? Internet of Things devices running on battery. We need this battery to last for long. And to last for long, we need to make sure that we don't consume much. Lower implementation complexity, the same. Lower complexity means your battery can last longer, your processing power can be used for longer period of time. and it's very critical for Internet of Things scenario. Higher network spectral efficiency. Maximize spectral efficiency across users and base station. Enable multi-user MIMO. You need, even for the cases when you have more users than the resources you have, what do? More users than the resources you have, what do? You need to come up with techniques, you need to come up with ways to accommodate those users, because you don't have enough resources. Link budget and capacity trade-off. We need to maximize it so that we increase the coverage range. Lower overhead. We need to reduce it as much as we can, because overhead increases the complexity of the network. We need to minimize the protocol overhead to improve scalability, reduce power consumption, and increase capacity. This is the OFDM. Everybody now familiar with OFDM? Everybody like OFDM. Everybody likes it. Yes, who doesn't? Anybody is not using OFDM in his phone or with the base station? Everybody's using it. But anybody knows anything about it? No. OFDM is our friend. We must get along with him. Make sure that we are comfortable with him so that we develop nice techniques that can improve it more. You have your data bits, coding and modulation, and then serial to parallel and your IFFT. This is the golden block, which is the OFDM basically. I explained it in the previous lecture how these are related to each other. And then you have the cyclic prefix. This block is this. These are the subcarriers coming from this block. How do you obtain them? We explained it mathematically last lecture with the matrices and this and that. Yes.
Is this also used, for example, for the army? They communicate.
Yeah, the army. Most all the wireless technologies used by army are basically mostly using OFDM. All. But they are not using the commercial networks, of course. And then you add cyclic prefix, and this is the way you add cyclic prefix. You cut the last part, you add it at the beginning, and you perform windowing. Why do we perform windowing? Question. To reduce out-of-band emission, to make it confined to certain band and be able to add more users within band. And this is your transmit waveform at the end of the day. OFDM family will suit it to meet the evolving requirements in terms of high spectral efficiency, lower out-of-band, asynchronous multiplexing, lower complexity, and lower power consumption. Now, we have different waveforms, means different candidates to meet the requirements of 5G, including CP-OFDM with WOLA, WOLA windowing overlap addition, single carrier frequency division multiplexing plus WOLA, universal filtered multi-carrier, filter bank multi-carrier, zero-tail single carrier FDMA. Now you have this block diagram. I want you to understand how to read this. You have this block diagram, yes? Now this block diagram, we call it A. If it is available in CP-OFDM waveform, we put tick here. If it is not available, we don't put. This block, we call it B, denoted by B. This is IFFT, this is block C, this is D, this is E. CP-OFDM, does it use this block, zero tail band? Putting zero at the end, at the edges? Yeah, but in OFDM we don't use. That's why we don't put any sign here. We don't put. Do we use DFT precoding? In CP-OFDM we don't. Do we use IFFT?
Yeah.
Of course we use it. Do we use CB? Yes, here CB. Do we use windowing? We bought it. Do we use band pass filter? We don't. This is basically CB. Now single carrier FDMA. Single carrier FDM with WOLA. Do we use DFT precoding? Yes. This is the key difference between OFDM and single carrier FDMA. Before IFFT, you use DFT at the transmitter, and at the receiver you do the same. After FFT, you use DFT. Clear? This is the difference. This is used in uplink in LTE, and this is used in downlink. Do we use CB? Yes. Do we use windowing? Yes. So the only difference between this and this, that we use DFT before IFFT. Clear? The receiver is the opposite. Whatever you use at the transmitter, the receiver is opposite. Universal filter multi-carrier. It uses IFFT, it uses zero guard, and it uses band pass filter instead of windowing and this. Filter bank multi-carrier, just IFFT and windowing. Zero tail uses the first three steps. So if I tell you draw zero tail single carrier FDMA transmitter, what do you draw? Zero tail, DFT, OFDM, IFFT, and then to the channel, to the RF. If I tell you draw this single carrier FDMA, you put DFT, OFDM. Now you understand the differences between these waveforms. These blocks are optional based on the waveform you use. This is main. Now we have single carrier waveform and multi-carrier waveform. Single carrier, you have only one carrier. Multiple carrier, you divide your whole bandwidth into sub-carriers. Now, what are the advantages and disadvantages of single carrier waveform? Now, what are the single carrier waveforms? We have 5 of them. First, constant envelope waveforms. Where do we use them? They are used in 2G, Gaussian minimum shift keying, and Bluetooth or Zigbee, minimum shift keying. What's the advantage of them? Zero peak to average power ratio. Very nice. Constant envelope, we call them. The peak to average, the power is always the same. Amplitude is always the same. No fluctuation. Allow asynchronous multiplexing. You don't need to be orthogonal. Good side loop suppression, low side loop. What's the disadvantage? Lower spectral efficiency. The second single carrier waveform, we call it SC-QAM, single carrier QAM. This is used in UMTS, which is kind of 3G. It has low peak to average power ratio. It's similar to the previous one, allows asynchronous multiplexing, and it allows simple waveform synthesis. What are the disadvantages? Limited flexibility in spectral assignment, and doesn't support MIMO easily. The third waveform, single carrier waveform, we call it single carrier FDE. Now I'm gonna talk about the structure of each one of these, how to draw it at the transmitter and receiver, but now we discuss only the advantages and disadvantages. This single carrier FDE, equivalent to single carrier QAM, but with CB. You add CB at the end. Allow equalization in the frequency domain. The disadvantage, adjacent channel leakage ratio is similar to DFT spread OFDM, which means a little bit high. Leakage, adjacent channel leakage is due to side loops also. Yes? Now the fourth waveform, which is single carrier FDMA, which is used in current LTE by your 4G, all 4G mobile phones, they use single carrier FDMA in the uplink. When you send a message, when you upload a video, they use single carrier. The advantage of it, flexible bandwidth assignment, allow frequency and equalization in the frequency domain. But the problem, high peak to average power ratio, needs synchronous multiplexing. And last waveform, single carrier waveform, zero tail single carrier FDM, flexible bandwidth assignment, no CB but flexible intersymbol gap, better out of band emission suppression than the previous one. But the disadvantages need synchronous multiplexing, need extra control signaling, lack of CB makes multiplexing less flexible. So these are the key advantages and disadvantages for the waveform related to single carrier. In the standard, they studied all of them, investigated advantages and disadvantages, and thinking which one to use. Now, the waveform based on multi-carrier, not single carrier, multi-carrier. You have the CP-OFDM, which is used in LTE 5G. You have the CP-OFDM with windowing. The key advantage here over the previous one is low out-of-band emission. All process of CP, all the advantages of CP, better out-of-band suppression than CP, and simple processing. You don't need complex structure to achieve low side loops. Universal filtered multi-carrier, better out-of-band leakage, but unfortunately it's sensitive to ISI and its complexity is high. Filter bank multi-carrier, better than CP with WOLA, but when you go to power amplifier nonlinearity, you lose the performance improvement over CP-OFDM, but the disadvantages are many, including complexity in the transmitter receiver, integration with MIMO is difficult, subject to ISI. Generalized frequency division multiplexing, same leakage suppression as CB, means out-of-band emission is low, but the disadvantages are many, including complexity. As you can see, the disadvantages mostly complexity, overhead, high block processing, complicated receiver, mainly about complexity and whether they are robust against interference or not. Now, this GFDM produced by German researchers, so Germany behind it. This filter bank multi-carrier, I think France, Universal filtered multi-carrier, European Union in general, and this CP-OFDM with companies from Qualcomm and Huawei and this behind it and Ericsson. So means the competition from all over the world to bring a novel waveform that can meet the requirements. Unfortunately, everybody was, some of them, they were designing OFDM waveform or better without caring much about complexity. In the standardization, they eliminated all the waveforms that cause too much complexity. We don't want them. So the waveform that can provide good performance, not necessarily superior or best, but with low complexity, they take it. Why? Because we are in the era of Internet of Things, in the era of power, in the era of reducing complexity, reducing delay. So you understand me? That's why. Now don't repeat this mistake again while you are developing an algorithm or developing a waveform during this course. If it is so complex, better avoid it. Think of something more efficient. Complexity, if you are gonna sacrifice complexity, you must gain too much that you can justify your complexity. What about the multiple access techniques? Single carrier FDMA used in LTE uplink. OFDM-MA in LTE downlink, single carrier RSMA, OFDM-based RSMA, LDS CDM, and multi-user superposition. Multi-user sharing access. Now, each one of them has advantages and disadvantages, but all of them were proposed. Some of them, they have peak to average power ratio issue, some they have intercell interface. In terms of advantages, each one has advantages, of course, because if you don't have advantages, you wouldn't have proposed it, yes? But also on the other side, you have disadvantages. So the one who has the maximum advantages and minimum number of disadvantages can convince the market. As you can see, And there are sometimes the authors, the producers, the inventor of the technology, they don't mention all the disadvantages. Sometimes they know and they hide, sometimes they really don't know. That's why you go to the standard and you give it to specialized company to analyze it. Because maybe you are missing something, you didn't analyze it or you didn't think of it. Other will come after you and analyze it and see it. So it's very serious and difficult, tedious evaluation process that consumes lots of resources to verify these claims. You say yours is less complex. Prove it. They come. You prove it and they come after you and you prove it again by themselves. So basically, waveform comparison, if you were to compare them, all these waveforms, in terms of high spectral efficiency with efficient MIMO integration, lower out-of-band emission, enable synchronization multiple access, lower power consumption, lower complexity. You can see that for single carrier equam, it's good in all except spectral efficiency. Single carrier FDMA, good in all except spectral efficiency. Zero tail, good in all except in synchronization and spectral efficiency. CB-OFDM, good in all, but it's not power efficient, and because of peak to average power ratio, and also synchronization, has synchronization issue. UFMC and GFDM, actually they are out of comparison. You cannot compare with them there because they are failing, as you can see here on the table. So due to the importance of spectral efficiency, we couldn't choose any one of these, although they are very good in the other parameters. So this high spectral efficiency, the weight of this, 50%, the weight of this, or 60. Like question 1 has 60 grade, question 2, 10 grade, question 3, 10, 10, 10. So the one who's good here, most probably you are going to select 10. Yes? OFDM, luckily, in spectral efficiency is good, that's why they selected. Although he's getting maybe 0 here, 0 here. But this is 10%, not that important. With 0, 0 here, he's getting 80 out of 100. But here, with 0 here, 0 here, 0 here, they are 40, 40, 40. So it's not by the number of checks. True, it's by the weight, the importance of the factor you are considering. Clear? Now you convince yourself why OFDM? Somehow? I think this is the main reason. But are we satisfied with OFDM? We are not quite satisfied with it. We want to improve it more, actually, more and more if we can. We are aiming to improve a little bit during this semester, during this course, hopefully. I will show you some techniques that we can do to improve. So, summary of recommendation that Qualcomm company provided to the standardization body, that enhanced mobile, for the case of enhanced mobile broadband, you have uplink and downlink. The key requirements, they mentioned the key requirements. This table is very important. This teaches you how to propose your technique for certain use case. You say, you tell us, ITU, International Telecommunication Union in the world, they want the future communication system to support enhanced mobile broadband. Dot. What does this mean? In the uplink, you need low peak to average power ratio, technically, low peak to average power ratio, small cell, high spectral efficiency, and many other requirements. Now, these are the requirements. You study the available techniques. Which one can meet these requirements? If there is, say, if there is nobody, invent, come up with your own. So they do this. You will do the same. You will say, they want in 6G to support this. These are the requirements. These are the proposed technologies so far in the literature. This is what I'm proposing. This is how will you do it. In enhanced mobile broadband, we said downlink CB-OFDM, uplink single carrier FDMA or CB-OFDM. Wide area Internet of Things, uplink single carrier FDE, downlink is CB-OFDM, higher reliability service, which we call it ultra reliable low latency communication. Downlink you have CB OFDM, and uplink you have single carrier FDMA with different waveforms. And here the requirements, and here the recommendation waveform that can meet these requirements. This is what will you do in your project, and this is what we are trying to teach you in this course. How to identify a new use case, new application, write its requirements technically, and then see if there is anything in the literature can meet this, and if there is nothing, you come up and produce your own technology, and you patent it. I will show you how to patent your ideas, because patenting is the only way that can make it legal for you to claim your idea. You cannot claim it sometimes by publication, and they don't consider it by law and this and that. So basically, and then after you patent, what do? You email the companies, you work as marketer now. You email the companies, you tell them, hey, you want to design this, I have this. If you are interested, I can license it for you. What's the price? You negotiate with them. Okay, this is not like software or application. You gain just $500 or $10, or you understand me? This you are talking about millions here, because it's affecting the standardization body. But you need to be able to convince. One student takes this seriously can graduate rich. I will teach you the process, how it works, and then you learn it and you start doing it. So we stop here. Thank you very much for your attention, and continue after 10 minutes.